I almost spoke to the wrong microphone this evening. So, colleagues, welcome to this inaugural lecture. We've had quite a few in the Faculty of Natural and Agricultural Sciences already this year. So I think it's an exciting time in terms of inaugurals. Unfortunately, many of you know that the pandemic has not been kind on inaugural lectures. So it is actually fantastic to see everyone here this evening. I know it's a small crowd. And when I look at the first slide, I understand why. So hopefully, Thomas, will understand. Those of us who are not mathematicians will also understand the talk. I'd like to welcome specifically the Acting Dean of the Faculty of Natural and Agricultural Sciences, Professor Hendrik Swart, who's sitting on the stage this evening. I'd also like to welcome the Head of Department, Professor Christian Venter, who's sitting to my left. Welcome, Christian. Then I'd like to welcome the man of the evening, Professor Tomáš Vetrík. It's an honor to be here this evening with you, and we are looking forward to your talk. I have a second-year math student at home, so I'll have to explain some of the talk to him. Then I would like to say a special word of welcome to Casey Vetrík, who is Professor Thomas's wife. Welcome to you. I've missed you. Where is she sitting? There she is. So I hope that you will enjoy this evening with us, and thank you for your support. Then I'd like to thank all the staff members who are here this evening, all the students, all the postgrads, students from the Department of Maths and Applied Maths, and then I see some other staff here. I saw some from different faculties here this evening, so that is a very good sign. And anyone who is from outside the university, I hope that you enjoy this evening with us. With that, I'd like to ask Professor Swart to present this evening's presenter. Hendrik?
Thank you. Good evening, everybody. It's my privilege to present Tomáš Vetrík to you. Now, as this is an evening of mathematics, I want the audience to sit back, relax, and feel the same as Leopold Kronecker, the famous German mathematician, who said, "Music is the finest of all the fine arts, with the possible exception of mathematics, which is superb poetry." We invite you all to an evening of poetry and mathematics. Tomáš Vetrík grew up in Slovakia. I presume it was high school. He was a member of an athletic club. Except for running, he also likes other sports such as cycling. When he was 18, he decided to do his BSc and then MSc studies in a town called Nitra at the University of Constantini, the philosopher. As he was too shy to go to the capital, Bratislava, he obtained his MSc degree in 2004. I googled the town. The oldest archaeological find in the last 5,000 to 7,000 years. He obviously lost his shyness as he then enrolled for a PhD at the Slovak University of Technology in Bratislava. During his PhD study, Tomáš received 2 scholarships from foreign countries. He spent 1 semester of his PhD study at Vienna University of Technology in Austria and 2 semesters at the Technikon Israel Institute of Technology. He was actually the only postgraduate student from Slovakia who got a scholarship from the government of Israel in 2006. He also spent some time at the university in Czech Republic during his PhD study. He completed his PhD study at the Slovak University of Technology in Bratislava, Slovakia in 2008. He likes going to developing countries, and in 2008 he went for a postdoc research in Indonesia. Tomáš then moved to South Africa in 2010, where he was a postdoctoral researcher at UKZN from 2010 to 2012. He then worked at the University of Pretoria from 2012 to 2014. In 2014, he accepted a position as an associate professor at UFS at the age of 32, and then became a full professor in 2020 when he was 38. He achieved this because of his extreme dedication. As he said himself, when he's in South Africa, he spends most weekends in his office. He met his South African wife, Casey Megan, maiden name Blomkamp, in 2014, and they got married in 2019. Casey is a lawyer, notary, and conveyancer. She is in the final year of her PhD study in law at UFS. By far, Casey's biggest hobby is horse riding. She has been riding horses since she was a child, and she competes in the main eventing competitions in South Africa. Eventing is a combination of 3 disciplines: dressage, cross country, and show jumping. Thomas and his wives are cat lovers, except for 2 cats. They also have 4 chickens and 1 horse. Since they are rarely at home, they do not even have a TV. And then, I must tell you this, there's a lot of pressure on tonight's caterers. Thomas likes to eat 3 breakfasts, 3 lunches, and then he will go out for supper. Every evening you'll find him in a restaurant. I have seen him in a lot of restaurants in the past. He's also a very practical person. When he arrived here, he was very cold, and he got, those old oil heaters. And after a while, he asked Marinda, where do I replace this oil of this oil heater? So that's how practical he is. Back to seriousness, his research area is graph theory, and he focuses mainly on the degree diameter problem, graph indices, and metric dimensions of graphs. Thomas has been an NRF-rated researcher since 2014, and he regularly received NRF grants. He has produced about 75 research papers, about 25 of them as a single author. 3 PhD students and 3 MSc students have completed their studies under his supervision. He also supervised 4 postdocs. He has presented seminars, talks at 24 universities from 15 different countries. He's an editor for 2 journals, and he refereed papers for 48 different journals. Interesting, one of Thomas' aunts, who is already 68, is also a dean of a faculty in Slovakia. The topic of Prof Vetryk's lecture is extremal graph theory. Most of us normal mortals, do not understand advanced mathematics. But I'm sure that, Thomas, you will illustrate to us tonight how uncomplicated, very complicated mathematical issues can be. How did Kronecker say, poetry in motion? Professor, congratulations on all your achievements. We are looking forward to your lecture, and good luck. Thank you.
Thank you very much, Professor Swart, for a very nice and long introduction. And yes, so my talk is about extremal graph theory, which is my research area. And since this is talk not only for mathematicians, many of you even don't know what is graph. Maybe when you say graph, most of you think of something which has x-axis, y-axis, but just that these graphs share a name. So our graph in graph theory is something which consists of vertices and edges. So as you can see, first the example is presented there. That graph has 8 nodes. So those nodes, again in graph theory, we call them vertices. So one vertex and many vertices. And those connections between those vertices, we call them edges. So I will talk about vertices and edges. So a graph consists of vertices and edges. The graph which is presented there has 8 vertices. And if you try to count the edges, you would find out there are 17 edges. And I want to just define some basic parameters which I'm going to use. They are really quite easy to understand. So first degree, then distance, and then diameter. So the degree of a vertex is the number of edges incident with that vertex. What does it mean? If you look at that vertex which is on the, completely on the right side, that one has degree 1 because it's connected only to one other vertex. The one next to the first vertex is of degree 2 because it is connected to 2 other vertices. Okay, so I think the degree is quite easy. Now the distance. The distance is also quite easy as it's mentioned here. But in graph theory, the distance is the number of edges which are between the 2 vertices. Let's say if you take the vertex which is completely on the left side and completely on the right side, how many edges do you have to take to get from the one from completely on the left to the one completely on the right hand side? Well, the easiest, the fastest way is to take only 3 edges. Therefore, the distance is 3. And the diameter is the distance between the furthest vertices. So which are the furthest? Well, for example, the one completely on the left and one completely on the right. Those are of distance 3. You will not find 2 vertices which are of distance more than 3. Therefore, the diameter of that graph which is presented there is 3. Let me just give you one more example. So we are very confident with the definitions. Thank you. So let's just look at this. Actually now, since it's closer, I can illustrate it even easier. Let's again look at those parameters which are defined. So let's say, how many vertices do we have now? As you can see here, I try to illustrate that we have n minus 5 vertices here, plus 1, 2, 5. So we have now n vertices in total. And again, it's easy to calculate also edges, since there are n minus 5 vertices here. Obviously, there are n minus 5 edges, plus 1, 2, 3, 4, 5, 6, 7, plus 7 more. So you will have n minus 5 plus 7, which is n plus 2 edges. Now again, the degree, for example, the degree of this vertex is 4 because it's connected to 4 others. The degree of all these ones is only 1 because each of these one is connected only to this one. So the degree is the number of connections. Now, distance again. So for example, the distance between these 2 is only 1 because they are connected. The distance between these 2 is 2 because you need to take 2 edges to come from one to the other one. You might be thinking, why the distance is 2? Why is not 3? Because we can go even this way. The distance is the quickest way how you can get from one vertex to the other. And the diameter, which is mentioned here, but also actually above, it's the same. So the diameter is the distance between 2 furthest ones. Diameter in this graph is 2 because every 2 vertices are of distance at most 2. So the diameter is the distance between 2 furthest vertices. And now I'm going to come to start with this problem, degree diameter problem, which is one of the 3 extremal problems which I would like to introduce to you today. So as you can see, we can use graph theory for very practical questions. And one question is mentioned here in this motivation. Suppose that we want to set up some network, and network satisfying 2 limitations. And the limitations are described there, and actually the limitations which are described there are actually the degree and diameter. Therefore, it is called the degree diameter problem. Because if we want to construct large networks, we are usually having some limitations. And what are those limitations? Obviously, if we have, let's say, large networks of computers, we can't connect one computer with too many because there are some constraints. We don't have enough cables or whatever, if it's telecommunication network or computer network, we always have some constraints. So let's have actually a little bit simplified example. If we study how many computer has the largest network, satisfying the following 2 conditions. Every computer can be connected with at most 3 other ones. And every 2 computers are either connected by edge or if they are not connected, they are connected through one other computer, which actually says the diameter is 2. Every two computers either connected or there is connection through one other. So, equivalent question to what is mentioned here, the practical problem, find the largest graph satisfying these two conditions. Degree 3, because connected only to 3 others, and diameter 2. Okay, maybe if you have a paper, you could start trying to find out what is the answer, and maybe after some time you would figure out you can't get more than 10 nodes in such a network, or you can't have more than 10 vertices in a graph for those two parameters. Really, you can check every computer or every node in a network is connected to 3 others. And if you pick any 2 nodes, any 2 vertices in this graph, they are really either connected, or if they are not connected, you will find one such that they are connected through that one. If you pick this one, you will find they are connected through this one. So if you pick any 2, if they are not connected, they are connected through one more. Therefore, the diameter is 2. Okay, even simpler question, if I would give you a question, find the solution for the parameters, both of them to be 2. How many nodes, how many vertices in a network at most can we have for degree 2 and diameter 2? And this one is actually even easier. You would easily find out for this network the maximum number of nodes in a network, the maximum number of vertices in a graph is 5. Really, you can see degree is 2. Every vertex is connected to 2 other vertices. And the diameter is 2. Why its diameter is 2? Because every 2 vertices are of distance at most 2. And in general, so I showed you example for very particular cases when the parameters are so small, 3 and 2 or 2 and 2. But this degree diameter problem is to determine the largest possible number of vertices for general parameters, not for 2, 2 or for 2, 3, but for given d and k. So let's say if d is some number, let's say 1 million or even much larger, and if diameter is also some large number, what is the maximum number of computers we can have in such networks, or the maximum number of vertices in a graph? Computer network is just one possibility, one illustration of the problem. So, and why is this an extremal problem? Because we are looking for some extremal graph, for some optimal graph, which is very large and which is, let's say, best possible. Well, maybe it's surprising for you, but for most DNK, actually for almost all DNKs, we don't know what is the largest graph. We can just find some constructions, which will give us lower bounds on the problem, or to prove that something too large is impossible. This is very theoretical upper bound. Actually, we know that it's not possible to construct a graph which has more than this number of vertices. It looks a little bit maybe complicated for non-mathematician, but if you would actually check what is this value about, it's about d to the power k. This value which is mentioned here is about d to the power k. That is a theoretical maximum. As you will see from some results, the known results are actually very far from the theoretical maximum. The graphs which are actually equal to the upper bound, Moore bound, are very rare. They are known only for trivial cases. Those trivial cases are complete graphs. Complete graphs are simple graphs which are such graphs that every vertex is connected to every other. So if you have 7 vertices, each of those 7 will be connected to the other 6. So complete graphs, trivial graphs of diameter 1. Cycles, again, we had a cycle just there, you can still see it. Cycle C5 is also extremal graph. Cycle C7, every cycle with odd number of vertices is an extremal graph. There you can see one of such examples. Except for these 2 graphs, and Petersen graph and one more graph, there are no graphs which actually can achieve the Moore bound. So then we study the problem, and actually I studied this problem using group theory, which is the graphs using actually groups which are called Cayley graphs. You don't really have to worry about the definition. We are not going to go some deeper into it. But just I want to, for those who are working in the area, in algebra or group theory, I just want to tell you what is the Cayley graph. Even if you don't understand what it is, it's absolutely fine. You will be still able to follow the talk. And now I study this problem for Cayley graphs. So I want to find the largest number of vertices in a Cayley graph for the degree d and diameter k. And again, I just will present few results just for you to see what is it about, like what we are trying to do. You can see here the first result which I obtained in this area still with my collaborators from Slovakia and New Zealand. When we found the construction, general construction for given d and k, which had this number of computers or this number of vertices in a graph. So obviously if I want to improve it, I want to find some larger construction. Why am I saying greater or equal to? Because if I find the network having this number of vertices, maybe somebody in future will find larger one. So they can improve the bound. And here I want to show you how actually one can improve it. So obviously, then later I was trying to study this problem by myself after I left Slovakia, and I found out actually if I just pick diameter 3, then I was focusing on special diameter, I could improve it. You can see this number is larger than this number for k equals to 3. If you replace this k by 3 and compare it with this one, you will find out this one has more vertices. Similarly, for diameter 4 here I could improve it. For diameter 5 I could improve it. So I was focusing on special value, and you can check these numbers because actually this -7, -8, -3, that doesn't really matter if you are going with d to be very large. It's about d to the power 3, and this is the constant. D to the power 4, and this is the constant, obviously 5 to the power 4. And here 4 to the power 5, but 25 divided by 4 to the power 5. So this was my result in this area, and this is the paper where my results appeared. Then I also studied, again, even maybe more specific graphs called cyclic Cayley graphs. The largest number of cyclic Cayley graph of given degree d and diameter k. Cyclic Cayley graph is a Cayley graph which comes from cyclic groups. Again, I'm not going to go deeper. Let me just present some results. So again, CEC means we are studying cyclic Cayley graphs. And again, I actually in this talk mostly want to focus on a result where I could slightly improve the results of other mathematicians. Because if I just state you my result, then if I don't compare it with something else, maybe it's a little bit difficult to see what is the impact of the result or why is it useful. So for example, in this case, I could also slightly improve the bound of others. If you would check 9 divided by 25 and 13 divided by 36, you would find out that this one is slightly bigger number than this one. So I could construct something which, if you go with d to infinity, then the value is slightly larger than the result of the other mathematicians. So again, the paper from this area appeared in this. This result appeared in this paper, and here I just slightly illustrate what group I was using for my construction. Again, this is maybe only information for 2 people sitting here who actually are working in that area. And then I actually studied this problem also for hypergraphs. And hypergraphs are actually not even graphs. They are more general structures. And actually this is the direction where I want to go in the future, because hypergraphs are more general networks. Actually it's defined with the help of sets. As you can see, hypergraphs have vertices, same as vertices of a graph. But what about normal graphs? Normal graphs, edges, is just pair of 2 vertices. Pair of 2 vertices, edge, they are connected. But in hypergraphs, any number of vertices can actually be hyperedge. So sometimes 4 vertices can create one hyperedge. 5 vertices can create another hyperedge. So it's more actually going more direction into set theory. So we have also some results in this direction with my former postdoc supervisor, Peter Dunkerman, who is now in Johannesburg. And I also studied different types of networks. So here we studied closed graphs and hypergraphs, but I just wanted to tell you that I was studying actually this degree diameter problem for various other networks, as here directed graphs, because in graph theory we have undirected or directed graphs. So for directed graphs I have a paper with my collaborator from Slovakia, with Marcel Abbas, and also one of my own single author papers, which is again about bipartite Cayley graphs. So again, special type of Cayley graphs, which are coming from various groups. So that was the first problem which I wanted to mention. I want to mention two other problems which I studied in my research. Well, obviously I studied more than these three problems, but I just picked three which are maybe nice to illustrate. So another one is called metric dimension of graphs. So again, there are a lot of applications of this metric dimension, because one possibility is in robotics, where the robot always needs to know its own location, where it actually is. And the easiest way is that you can represent the network where the robot can move by a graph. And how to represent actually the space for the robot. So let me just give you some example. As you can see, assume that we have again something very simple, like simple network, which is just described here. So in a metric dimension of graphs, first we should define something called resolving set. So resolving set is a set such that any vertex will have unique representation in terms of distances. Again, let me just give example and you will understand it very easily. It's very simple. So I'm asking, can this vertex by itself be a resolving set? And the answer is no, because if you study distances in terms of this vertex, you will see these two vertices have representation which is just 1, because they are of distance 1 from this one. These two have distance 2 from this one. So let's say if you have this robotics problem, and if a robot is here and he knows I'm at 1, he actually doesn't know if he is here or here. So you want to find the representation in your space, in your graph, in such a way that every vertex will have unique representation. 1 is not enough, okay? So this is not a resolving set, which is defined there. But if you pick 2, as you can see, I picked this vertex to be the first one, and this to be the second one. These two vertices do form a resolving set. Because as you can see, every vertex has unique representation. If the robot knows he is at 1, 3, he knows it's here. If the robot knows he's in the place called 3, 1, he knows it's here. So every vertex has unique representation in terms of distances, which means these two vertices form a resolving set. Therefore, the metric dimension of this graph is 2. So now we know the definition of metric dimension. It means every vertex in our graph space, has unique representation in terms of distances. Here is a little bit more background and some history about this problem, since this problem has been studied for quite long. From, as you can see, the first results are from 1975. And I want to just present again my results, or at least a little bit mention. So again, with my collaborator from Slovakia, Marcel Abbas, we have a result from 2020, where we presented the metric dimension, again for graphs which come from groups, which I mentioned earlier, which are Cayley graphs. The definition was there, therefore I mentioned the definition because I'm mentioning Cayley graphs quite often. So we studied Cayley graphs, and we presented results again in the paper which is mentioned here. And I want to describe easier graphs, which I also studied in my research, which are actually called circulant graphs. And again, circulant graph is a graph which comes from groups. It's Cayley graphs of cyclic groups. But let's take now very simple generators. So this means that the vertices, we will have n vertices, 0 up to n minus 1. And edges will be just also defined in a relatively simple way. If the generator is 1, you will be just connecting 0 with 1, 1 with 2, 2 with 3, and so on. If the generator is 2, you will be connecting, in general, Vi and Vi plus 2. If the generator is 3, you are going to be connecting Vi and Vi plus 3. Therefore, this graph is C8, Y8 because it has 8 vertices, Y1, 2, 3 because every Vi is connected to Vi plus 1, Vi plus 2, and Vi plus 3. The graph looks very simple, this kind of space which we are studying, but still the results are, it's very difficult to find exact values of the metric dimension. And as you can see, here is the result if just we have 2 generators only. Generator 1, generator 2. And here we have 3 generators. Generator 1, 2, and 3. So here you have exact values, but it was not that easy to find exact values of even these simple graphs, because the final result is from 2018, but actually this problem has been studied since I think 2008. So it took 10 years to complete all the values. Let's say, as you can see, for some values it's 4, for some values it's 5, but it was slowly. So first authors found value, let's say, for 3 or 4 out of these numbers which are mentioned here. And slowly it took 10 years till all the values were found. Obviously then, natural generalization of this problem is not to study 3 generators, study general number of generators. So that was what I was doing in my research, because I saw result of other authors which were trying to actually handle the problem for general T. And they proved that the value of this DIM, it means dimension, so metric dimension of this graph is always at least T plus 1. You can see that motivation is coming from there, because it worked for 2 generators and 3 generators. So they were hoping it works also for T generators in general. However, I found a gap in their proof. That actually, if you want to show that the dimension is at least T plus 1, it means if you take any T vertices in a graph, it will never work. You can't take T vertices and resolve the graph to have different representation. But as you can see, this is a counterexample to this result, because such small graph is sufficient to show that this result is actually not correct. As you can see, if you pick these 4 vertices, and from the definition of the graph you can even try it today in the evening at home, and the representation in terms of these 4 vertices, you will find that really the representation is different. So 4 vertices can resolve this graph. So it's not at least T plus 1. It can happen that T vertices actually will resolve the graph. And then I came with the counter result. So actually the dimension is sometimes at most T for some values which are mentioned here. So actually for every even T, I can have an infinite of family of graphs which are going to have the dimension at most T. And since this result doesn't hold, then I actually found that it's not true that it's always at least T plus 1, but it is true that it's always at least T. If the number of vertices n is actually sufficiently large, so if n is at least T squared plus 1. So if number of vertices is sufficiently large, then it can be actually, then it is always at least T, and since it's at most T and at least T, then for some values which are mentioned in the previous results, it's actually exactly T. These results were from 2017, and you can see the paper is actually already mentioned here, where I published those results. But there was one more challenge, that actually there was a known conjecture where they assumed that actually the metric dimension is, for certain values, always T plus P minus 1. And I disproved that conjecture. You might be wondering why in 2017 and why in 2 years. Because actually in 2017 I handled to disprove the conjecture only for even P. As you can see, I disproved the conjecture for these values of P, which is for almost all, because the conjecture was valid for P being between 3 and T plus 1. So I managed to disprove the conjecture for all the P, but between 4 and T plus 1. In 2017, I managed to disprove it for even P, and in 2020, I disproved it actually for odd P, which means for almost all P. Why not for p equals to 3? Because as you can see, my bound here is equal to the value there. So I don't know if by chance it's less or not, but if you replace p by 3, this one and this one is the same number. Okay, and my two papers in this area are mentioned here. Here are the references. So these two papers are about that topic. Let me also mention there is a parameter which is called partition dimension of graphs. And we obtained with my former PhD student, Elizabeth Maritz, also very strong results in the partition dimension. So yeah, these problems are related. I didn't mention partition dimension here because I just picked the one which has like a little bit better applications, which is a metric dimension. But yes, with Elizabeth Maritz we obtained similarly strong results afterwards also about partition dimension, because I could see also that there are gaps also in that area. Now the last problem, and I think it will be the fastest to go through this one, is indices of graphs. Okay, indices of graphs, there are quite a number of them, but the most famous one and the first one is the Wiener index. And these indices have actually application in chemistry, as it is described here, and they have been studied from 1940s, so very long ago. And this index has actually very, very simple definition. The Wiener index is just sum of the distances. Again, what are the distances? Distances for vertices. So in your graph, you will pick every pair of vertices and we will calculate the distance. Every pair of vertices, distance between these two. So let's say if you have 3 vertices, it's very easy because you will, let's say, calculate distance between, if there are 3 of them like this, distance between these two, distance between these two, and distance between these two, and you will just sum them, plus. So you will have actually 3 numbers, sum of the 3 numbers will give you Wiener index. Different name of this Wiener index in literature is average distance. So if you are looking for results about average distance and Wiener index, it's the same, but doesn't matter. Again, we are not going to deeper into it. I just want to tell you what I'm doing in this area. So another index which is very heavily studied, one of the most famous indices, is called the degree distance. And the degree distance is defined again for any 2 vertices from a graph. VG stands for vertex set of vertices of a graph. Pick any 2 vertices and do this rule for them. Calculate degree, calculate distance. That is the degree distance. And then I found out there is also a little bit less famous, but still studied quite a bit, reciprocal degree distance, which is defined in this way. And then I got an idea. If you look at 3 of them, you can actually introduce a general parameter, which will cover all 3. So, very recently, last year, I introduced a parameter called general degree distance. Well, as you can see, it generalizes, and as I will show you very soon, all these 3 indices which were studied for very long are actually subcases of this one which I study in my research. And if you actually pick A is equals to 1 and B is equals to 1, you will get the classical degree distance, which was defined just there. If you pick A is equals to 1 and B is equals to -1, you will get the reciprocal degree distance. And if you will pick one parameter being 0, the first one, you will get twice the Wiener index, which studying the Wiener index or twice the Wiener index is the same. And then actually I found in the literature there is also an index called Harari index, which is again obtained for A is equals to 0 and B is equals to -1. So the advantage of studying the general index, that sometimes you are able to get a result which will hold for all the other indices. So actually you don't need to study them separately. You can study them using maybe one method. Obviously many times you are not that lucky and the same method will not work for more indices, but often it will work at least for 2 or 3 of them. So that's what I studied in this paper. So I defined this new general index only last year in 2021. And a little bit simpler indices are, so this one was involving distances. And this index, which is mentioned here, was known, as you can see, from 2010, and it's called General Sum Connectivity Index. And actually, therefore, I got the idea to generalize the more complicated distance-based indices, because I could see that degree-based indices were studied in general way, but not distance-based indices. So therefore, I just introduced also general way of studying distance-based indices, because since it was done for this one, the advantage of here, since you are studying only degrees, you have only one general parameter. Here it's more complicated because you have two general numbers, A and B. Here you have only A. And let me just, as my last result, show you my result in this area. So, as you can see, this index is studied for ages. So, VW belongs to age set. So, you are looking for every ages and calculating the value. Calculating the value for first age, for second age, and for all ages in the graph. And then you will get the final value. And again, this index, what is presented here, is a general index defined in 2010, and it is actually generalizing, again, quite a few indices. Not only two, I mentioned only the two because my general result is actually studying these two values, because the general result, what I'm going to show you, my one, is for the values between -1, including -1, and 0. So it's covering these two particular indices, which are also very famous indices and were studied a lot. Many people, actually chemists especially, are studying very applicable problems. I'm a mathematician. I'm mostly going for theoretical mathematical problems. But anyway, let me show you my result in this area. It's my last result which I want to present. It's actually a result from this year, where I presented some bound. Actually, usually I present the bound. In extremal graph theory, we present bound in terms of the value. But I didn't put the value of this graph, so this is the value of index for this graph. This is too general graph. I decided not to try to define it here because it would take long. And the reason why I didn't present the value of this graph, so this is some value. But actually the value is quite different for many parameters. So if you take, let's say, k is equal to 3, the value would be different than k is equals to 4. So I would have to define many cases here. But anyway, this is the extremal graph. Sometimes it has different value, but the extremal graph is always this one. Now, corollary of this result is actually this result, because then I was studying, here I presented extremal value for studying two parameters. Diameter, which I already defined, and girth. Girth is actually length of the cycle. Unicyclic graph means graph which has exactly one cycle. So here I studied graphs which have exactly one cycle. Also, these unicyclic graphs are studied because they are very applicable and they can actually be used for chemical structures, because a lot of chemical structures have one cycle. So unicyclic graph which has one cycle, girth is the length of that cycle. So I presented the value extremal graph. Now I wanted to obtain the result only in terms of k, not for k and g, only for k. So I had to just again minimize it because I'm looking for minimal graph, and I found that actually the minimal value is achieved for g is equals to 4. As you can see, here g is anything greater than 3. Minimal out of the values is g is equals to 4. So this is kind of a corollary of this result. It still needs quite some proof, but it comes nicely. And now, as you can see, my result is for between -1 and 0. So those two classical indices which are mentioned there, again, are results on those indices are corollaries. So one corollary will be for a equals to -1/2 and one for a equals to -1. So this one is corollary of that one. This one is corollary of this one, because you just pick a is equals to -1 and you will get this value. Why I have value here? Because for this graph, as you can see, the value is already mentioned here for this graph, which actually you don't know how it looks. But if you pick a is equals to -1, you will get this value. So this is kind of a double corollary. And the reason why I just picked this result to show you, this double corollary is still a big generalization of a result of other people. These two mathematicians presented two papers. This is result from one of their papers, and this is result from another of their papers. And I want to show you that this one, very easily from this one, both of these results follow. And how? That's a bit short proof. And for that proof, we just need to know, which you actually don't know, that for unicyclic graph, or for any graph which is not a very simple path, the diameter is at most n minus 1, n minus 2, where n is the number of vertices. Number of vertices in a graph, minus 2, diameter will be never more, if the graph is not a path. So again, diameter is at most n minus 2, where n is the number of vertices. Using this simple result, which everybody knows, you can easily find out, if you use my result and divide both sides by k, you will get the index divided by k is this one. And now, since k is at most n minus 2, then since k is in the denominator, you will get the opposite inequality, and you will get there one of the results. Actually, this is their second result. And here, exactly using the same thing, again, my result, minus k from both sides, you will get the index minus k is this one, and again, using this simple inequality, you will get also their first result. So, again, I chose to show you this one because, again, I can show you that I could do something which highly generalizes the results of other people. In the work where I presented these results is also mentioned this. Actually, it's only published online. It hasn't been published in a volume and issue yet. That's all. I wanted to introduce 3 extremal problems in my research. I hope you understood something. I thank you very much for attention. And I also maybe want to say, I also want to thank UFS and the mathematics department that I can be part of it for already 8 years. And I also like my wife and all my family for support during all those times. Thank you very much.
Thank you very much, Professor Vetrík, for that really insightful talk on graph theory. I didn't realize before tonight the amount of D's in graph theory. It's diameter, distance, degree, there was a dimension.
Yeah, therefore I had to choose different names. So usually we don't use K for diameter, but I couldn't use D because in my research I'm using degree and also diameter. If these 2 parameters are not involved in the same paper, both of them are D. Yeah. Degree, diameter, distance, all of them are D.
Yeah. It's maybe a conspiracy theory on the D's, but the other thing I think we should call ISCOM and say we solved the problem. I see with all your generators that you've got going there, we shouldn't have any more electricity load shedding issues with all your generators. We can even choose them ourselves. When I think about Tomáš, I'm reminded about the words of a very famous graph theorist, Steffi Graf. I know it's spelled differently. Tomato, potato. What's
Actually,
the difference?
in my language, it's spelled the same.
It's oh, okay. Well, even closer.
So in my language, graph is having F.
In any case, Steffi.
It's not F.
It is with an F, yeah.
Okay.
Yeah, but in English, the PH it's not there, yeah. In any case, Steffi Graf, the graph theorist, she said, and I want to quote her, she said, "I have always been guided by striving to show the best that I could. That is what kept me going in tennis, and it is the same now. Striving to show the best that I could." I think that's Tomáš. And I think the talk tonight again showed that, the striving towards excellence. I think it's part of your core operating system. So thanks for that. But Tomáš, I don't think our colleagues are here tonight primarily to learn more about graph theory. We were here to support you, to celebrate with you. So congratulations on reaching the level of professor in pure mathematics at the University of the Free State.
Thank you.
Congratulations on that. Just a fair warning, the fact that you're now a professor, if you do get into an argument at home, you are still wrong. Maybe especially because you're a professor. Okay. Some thank yous, I think, in order now. First of all, everybody that was involved in the arrangements for tonight. Alicia Pinar, our events and protocol specialist from the Department of Communication and Marketing, a big thank you to you. And then our very own Miranda Venter from the Maths Department, a true pillar of strength. Thank you, Miranda. And then Roystool Video Publications or Video Solutions for the live streaming. We've got sound for the sound. We've got Charles Devenish for the photography. A big thank you to all of you. And then that ends the formal proceedings for tonight. You are all invited then for some refreshments in the foyer. Just give one moment then for Professor Vetrík and Casey to make their way to the door. We will meet them there and congratulate them there.
Thank you very much, Christian.
Thank you and good night.